heard this question well, talking about it. Do I believe in fate or free will? Is that what you said?
Yes.
Free will.
Free will it is.
Yep. Free will.
That's what I.
That's mainly because I'm a control freak. And I'd hate to think that I didn't have control.
Crystal Spencer, come to the office. Crystal Spencer.
Okay. Here we go. Woot, woot. Okay, so we're going to talk about discontinuities, which are things that caused issues with the domain. So like when you have a hole in the graph, when you have an asymptote, when two graphs just don't connect, things like that. Those are discontinuities. Anytime you can't trace a graph without picking up your pencil, it is not continuous. It has a discontinuity is what it's called. Okay, so for example, you can have things that do connect, like, do it like this. Whoa, not what I wanted to happen. That'll work. So these are like, this is like a piecewise function. You have two pieces of a graph. One is a quadratic and one is a line. But they connect. They connect not at an open circle, they connect at a closed circle. So they connect at a closed circle, that would be considered continuous, because I can trace that graph without picking up my pencil. Sometimes they connect at an open circle. So same picture. Hopefully, as much as I can make it. Only I have an open circle there. Then the closed circle is somewhere else. So that would be discontinuous, because there's that open circle, there's that hole in the middle of the graph. So I'd have to pick up my pencil to go from one part to the next part. And then you can have two that just don't connect at all at A. So this one's going to look a little bit different. So those two don't even touch. You follow it, you get to that point, and then you have to skip from there to here to follow it the rest of the way. So those are basically the three things that happen. You either have piecewise functions that actually come together and they touch, or piecewise functions that are connected by an open circle, so they don't technically touch, but they're pretty close. And then you have piecewise functions that are separated, that don't touch at all. So the last two, have what's called discontinuities. We have issues at A. So let's talk about first what it looks like when it is continuous, when they do connect with a closed circle. This is great review, by the way, because this is stuff we did, I don't know, not at the very beginning. So we have two functions for q of x, and what we're going to do is we're going to graph these two. Okay, so negative x plus 3 squared plus 4. And it goes from negative 5 to 0. So I'm going to make a little XY chart over here. And I'm going to go from negative 5 to 0. And I'm going to plug that into the top one. If I plug in negative 5, I get negative 5 plus 3 is negative 2. Squared is 4. But then there's a negative 4 there, or a negative there. So it's negative 4 plus 4, that's 0. If I plug in 0, I get 0 plus 3, it's 3. Squared is 9, but there's a negative in front of it. So negative 9 plus 4, that's negative 5. It's a coincidence that they're flip-flops of each other. So I have the point. Color code this. Negative 5, 0, filled in circle. 0, negative 5, that's an open circle. Just because it's just less than 0, there's not a line under it. I need another point on there. Yes, ma'am. Yes. So the plus 3 inside here. Well, first of all, what's that pink graph going to look like? A parabola. Good, because of the squared. And the vertex of my parabola is going to be where? Negative 3, so I go to the left 3 because of that. And what's that 4 do? Up 4. So it's going to be at negative 3, 4. Negative 3, 4. That'll look something like that. So over here this says the first piece of the graph of q of x, which q of x is that pink graph we just graphed, that parabola, will end just shy of x equals 0. And the reason why it's just shy is because it goes right up to 0, but never actually equals it. The second piece of q of x will begin at x equals 0. So that means it says of q of x, okay. So that's this point right here. Let me change colors so you can see what I'm pointing to. This point. So just like what we just figured out, I'm just filling in the blanks here. I start at 0 and I go really close to 0. I'm at negative 5 here, but 0 on the x. We good? Go ahead.
It says it begins at x equals 0.
Mm-hmm.
Wouldn't that be y equals 0?
Yes, it would be. Why is it saying x? Oh, the second piece. Sorry. That's my bad. The second piece, I read that wrong, is referring to this other graph. So that's the second piece of q of x. And the second piece is absolute value of x minus 2 minus 7. So I'm going to make me a little XY chart over here. And if I plug in 0, I get 0 minus 2. Absolute value of 0 minus 2 is 2. 2 minus 7 is negative 5. So that's saying the second piece, which is that green one, of q of x will actually begin at 0, -5, because it's got a line under it. So here, I would actually fill that in. So it is 0. I was just talking about the wrong equation. Okay, so in this spot here is what we just did over here. So is q of x defined at the x value where the first piece ends and the second piece begins? If so, find the value of y find the value of y at that x value. So what that means is, just like we already did, we plug in 0. Like we did. And so that's where that -5 shows up. That's where we got this filled in circle. Thank you, Gisela, for saying that. So the rest of that graph, I know, is supposed to be an absolute value function. What shape is the absolute value function? A V. Very good. So my vertex of my V is going to be where? What is that? Well, you just think it's at that point. Yeah, that's a +2. Because remember that -2 means that it moves to the right 2. And the plus or the -7 means that it moves down 7. So that's at the point